All right, so page 586, number 9, says Jupiter's moon Io orbits Jupiter once every 1.769 days. So the T, the period of Io, is 1.769 days, which of course we will have to change to seconds. Its average orbital radius, so RP, make that IO. RIO is 4.216 times 10 to the 8th meters, and it wants to know what's Jupiter's mass. So we're looking for the mass of the central body. So if you look at your equations, you have an R and you have a T, and you want the mass of the central body. So I would use Newton's version of Kepler's third law, this guy. Okay, so R cubed over T squared is equal to G mass, in this case it's Jupiter, over 4 pi squared. So take your 4 pi squared up, your G down, and you'll get the mass of Jupiter is equal to 4 pi squared R cubed over G times T squared. Fill in your numbers. 4 pi squared R is 4.216 times 10 to the 8th, and you have to figure out where the cube button is on your calculator. G is 6.673 to the negative 11 Newton meters squared per kilogram squared. And the period is 1.769 days, which you would need to multiply by 24 hours per day and by 3,600 seconds per hour. And then you would need to square it. Okay? And if you remember to square the pi, cube the r, square the t, if you could type everything in correctly, you should get a mass of Jupiter to be 1.898. I think it's really 1.8979 or something like that, times 10 to the 27th kilograms. All right, that's number 9. Number 10. Charon, the only known moon of the planet Pluto, has an orbital period, T of Charon, is equal to 6.387 days. Again, you're going to have to change it into seconds. And an average distance from Pluto so radius of the moon is 1.964 times 10 to the 7th meters. Use Newton's version of Kepler's third law. So exactly what we used up above, except this time they thought they'd tell you to be nice. They didn't tell you in the first one, but so R cubed over T squared is equal to G mass of Pluto this time over 4 pi squared. Rearrange for the mass of Pluto. Bring your 4 pi squared up with your R cubed. Take your G down with your T squared. Fill in your values. So 4 pi squared, 1.964 times 10 to the 7th meters cubed, divided by 6.673 to the negative 11 Newton meters squared per kilogram squared, and then 6.387 days times 24 hours in a day times 60, or times 3,600 seconds in an hour squared. And if you remember to square your pi, cube your r, square your t, you should get 1.472 times 10 to the 22 kilograms. It's about on par with the moon, and if we were in class and you looked at my wall, you would see that Pluto and the moon are pretty close to each other. Okay? And yet, then look at Jupiter. Jupiter's like 3 zeros. 1,000 times bigger, not quite 1,000 times bigger, about 500 times bigger than the Earth. All right, number 11. says some weather satellites orbit the Earth every 90 minutes. So the period of the satellite is 90 minutes, which again you'll have to change to seconds. How far above the Earth's surface is their orbit? Remember, okay, so here's the Earth, and this is the radius of orbit. This is big R. But this question is actually asking how far above the surface. They're asking for the height. And this is little r. So if we can find the radius of orbit, then we'll be able to find the height by subtracting the radius of the Earth. Okay, so we're looking for the r of the satellite, capital R of the satellite. We know it's the Earth, so you could use r cubed over t squared for the satellite is equal to g mass of the Earth over 4 pi squared, because we know the mass of the Earth. We know it's given in the chart. And we're looking for r cubed of the satellite, so take your t squared up. So r cubed of the satellite will equal g mass of the Earth t squared over 4 pi squared. So 6.673 to the negative 11 Newton meters squared per kilogram squared. Mass of the Earth, 5.98 to the 24th, and it's on page 955 if you haven't used it enough that you don't know it off by heart. And 90 minutes multiplied by 65,400 seconds squared divided by 4 pi squared. And when you go to divide by the 4 pi squared, make sure that you put it in brackets, okay? So you'll get an r cubed here, and then you'll need to take the cube root. The r cubed is 2.947 times 10 to the 20th, and that would be meters cubed. Take the cube root, and you should get 6.655 times 10 to the 6th meters. Okay? So that is number 11. Number 12 says, how fast is the moon moving as it orbits the Earth a distance? Oh, wait, I didn't finish. That was the radius of the satellite. We wanted the height. So the height would equal the radius of orbit minus the radius of the Earth. So the height would equal this 6.655 times 10 to the 6 meters. And then if you look in the back on that chart again, you'll see the radius of the Earth is 6.38 times 10 to the 6 meters. So how high is the satellite above the surface? 2.7503 times 10 to the 5th meters. And that is the real answer to number 11. Number 12. How fast? So we're looking for speed, v. How fast is the moon moving as it orbits the Earth at a distance? So the r for the moon is 3.84 times 10 to the 5th kilometers, which will be 10 to the 8th meters. So you're looking for v. You know it's the Earth and that it's orbiting. I'd be tempted to use this guy. Right? We know the central body is the Earth. They gave us the r. You could look up and find out what's the period of the moon, but that takes more work. So I would go with v squared is equal to g mass of the Earth over r. So 6.673 to the negative 11 Newton meters squared per kilogram squared, 5.98 to the 24th kilograms divided by the 3.84 times 10 to the 8th meters, right? Because 5th kilograms would be 8th meters. And remember that's going to be your v squared. You're then going to have to take the square root. So v squared is something like 1.039 times 10 to the 6th meters squared per second squared. And when you take the square root, you get a v of 1019.402 meters per second. Now, if you did it as 2 pi r over t, I think you get 1022, and the difference would be because of the rounding the mass of the